Hey everybody, welcome to the PC Perspective Mailbag, yet another episode. This one's going to be on storage stuff. Jim has been stockpiling all of the storage-related or storage-heavy questions off of the all the questions submitted, normally going to Ryan, but he's out of town, so I'm going to fill in and get through the backlog of storage stuff. If you have any other questions to go on a future storage version of this, or just to go to Ryan or anybody else that might take them in future mailbags, make sure you leave them in a comment below this video or in the post on the site if you happen to be watching this video on PCPer. Might as well get right into it. First question from Spoken Cabbage. Are there any disadvantages to using M.2 SSDs compared to normal SATA SSDs? For example, a 1TB Western Digital Blue M.2 costs about the same as a 1TB Blue SATA SSD model, but the M.2 has the benefit of not needing data and power cables, so why are they the same price? Alright, so the 1TB Western Digital Blue is M.2, and it's actually PCIe SSD. So the performance is in fact better than the SATA model. There's a better interface, there's more throughput available there, and it just overall better performing part. Why are they the same price? At the end of the day, though, as long as the controller is a reasonable price to the company that needs to buy it in order to put it onto the M.2 part, you know, in a lot of cases, especially now with more cost-competitive controllers, either on the SATA side and the M.2 side, in other words, M.2's been around for a while now, like the controllers are starting to come down in price, it's entirely possible that the cost to make these products is about the same. Now, there are some companies that will be able to get some further advantage of the much higher performance out of their NVMe M.2 parts. In other words, like Samsung 960 Pro. You're basically paying for the extra performance. That SSD is much faster than most of the other SSDs out there, including this 1TB Blue. But if you're looking for just, kind of like average performance or okay performance, for most folks, and the cost is the same, as long as you have a place to plug that M.2 part in, by all means, get it. Especially since you don't need data and power cables with M.2. It's just a much cleaner install, right? I'm almost to the point where I don't even have any SATA devices in my PC anymore. I have like one data drive connected just to hold some extra stuff that doesn't fit on the M.2 drive. So, yeah, I mean, it's a good deal. Take it. That's my point. Next one, Alchemerd. Sorry if I'm mashing up the names here, but all you guys spell your names so weird. Is it really necessary to have over-provisioning space on a SSD for a gaming PC, desktop gaming PC? Samsung Magician software automatically sets over-provisioning to 45 gigabytes on his 500 gigabyte 850 EVO. That seems like a lot. That does seem like a lot. I'm not quite sure why that software would default to doing that, or even try to get you to do that. Unless they're talking about the over-provisioning that's just kind of built in. But I don't think that software does that. I think that software counts 500 gig as if you like 100%, and you would just, go down from there. Yeah, you don't need that, especially on an Evo series drive. Reason I bring that up is if you look at our results from any of the recent consumer SSD reviews over at PCPer, and I think it was like maybe in the 750, the Samsung 750 review, I think I did a roundup of the 3 capacities of that drive. And in that review, I had not only results of our new test suite from that drive, but I had results of, I don't know, I think it was over 100 competing drives. Basically, we passed every single drive that we had through the new suite and got results. If you look at those results, first of all, they're pretty hard on the SSD. They fill it at varying capacities, so it runs, I think, up to on the order of like 95% full is what it weighs results based on like at least half full and even somewhat if you're like 90% full. So it's pretty torture test, like worst case scenario kind of stuff, for testing an SSD. And the 850 Evo doesn't care. It honestly doesn't care how full it is. The read performance doesn't change if you have more data on it. And the random performance, if it's random reads, same deal, doesn't really change. The issue where you would want better, more over provisioning for a given SSD is for random write performance. That's where the benefit is going to be the most noticeable. 850 Evo has an SLC cache on it. It doesn't really care about, as long as you're not doing random writes to it for an extended period of time and at the maximum speed the SSD can go, chances are you're not. Most SSDs are never going to see that kind of a workload outside of me benchmarking them. So yeah, I wouldn't set any additional over provisioning on any SLC caching SSD for one. And I honestly, if you're just doing it for a gaming PC where most of the time you're just loading games and such, I wouldn't really do it for even an MLC drive or any SSD for that matter. I personally have never, outside of just testing something for a review to see if there was a difference, I have never personally run additional over provisioning over what came on from the manufacturer, which is not adjustable. You can't adjust it to get rid of the little bit that they do put on there, because you need some spare area and things just need to work properly. So don't do that. I'm not sure if you have to like clean erase or secure erase the drive again to change that number through the Magician software. Hopefully you have somewhere else to put that data, and then you can do whatever you need to do to get that space back, and then feel free to use it. Next question, Rivo K. TLC NAND based SSDs have an SLC cache. Yep, we were just talking about that. What happens to data being written from the SLC cache to the TLC NAND in the background if I shut my PC off, or if the power fails before the cache is emptied to the NAND? Will the controller attempt to write data to the NAND chips in the background even when the PC is powered off but connected to power? Will data be lost? Or will the process continue in the background only after the PC is powered up again? You're kind of answering yourself there. That's basically what happens. So the last part at least. First of all, when the SLC cache empties to TLC or whatever the bulk of media is on the device, it happens first in such a way, especially if there's no power loss protection capacitors or any other extra things on the product to make it able to do things. First of all, even if there was a cache, like a large amount of SLC, the capacitors alone are not going to be enough for it to totally empty that cache. Capacitors are usually just to make sure that if there's something that needed to be juggled around, that the controller at least has enough time to finish that juggling of data that might not have been duplicated in multiple places. In this case, your data that you wrote is in the SLC cache. It writes to the TLC, and SSD controllers will tend to be smart enough to make sure that the data has been committed to the TLC. In other words, not just sent to the chip, but that the chip has acknowledged, okay, I have completed writing this to TLC, before it turns around and erases that section from the SLC. So it's careful about how it empties the cache to make sure that at any point in time the power can go away and it'll still be somewhere, right? SLC cache is still flash memory. It's still non-volatile. So it still has that benefit where if the power went away, whatever was written there is just going to stay there. It'll still be there when you power back up. And that's actually what happens. As part of its startup routine, the controller checks, hey, I had this little table that I was saving also in the SLC flash, and that table says that I still had 29 blocks to move over to the TLC, and it just picks up where it left off and finishes it. For a lot of SSDs though, especially Samsung, most recent like 850 Evos and whatnot, if you have a 500 gig or larger drive, the write speed to the TLC is actually faster than the interface. So for drives like that, 500 gig and up, when we test, we don't even notice a fall off. In other words, if we do a sequential write to them, it'll go full speed, and then it may very well be going to the cache, but when we run out of cache, we don't notice from our perspective of, the software that's evaluating the performance, because the speed just never changes. Now, I don't know if those drives skip the cache in those places, or the cache just stays fairly empty. It probably just stays fairly empty. Where the cache would come into more play for those drives is if you were hitting them really heavy with random writes, and that can't be written to the TLC as fast, and then they would buffer those for a while, and then eventually the cache would be full. So just keep in mind that, unless you catch it in the middle of writing data to it, not only writing data to it, but writing to it at full speed. And unless you have another SSD in your system and you just spend all day moving stuff back and forth, you're probably not even taxing the cache on the majority of these caching SSDs. The cache stays empty most of the time. All right, next up, Jim Anderson. Do you think the memory technology behind Optane will expand beyond Intel to become universally available for boosting hard drives on all motherboards or as supercharged SSHDs? Or does Intel have some sort of exclusivity deal with the memory manufacturer for a few years? Well, first of all, Intel has the best exclusivity deal with the manufacturer in that they are the manufacturer. So yeah, there's that. They are manufacturing jointly with Micron. Micron can choose to make some SSDs and put Crosspoint in them if they chose to. They have not chosen to for whatever their marketing reasons are. Maybe they don't see as much of a profit in it as they'd like just yet, or whatnot. But Intel is obviously pushed forward. We have products from them. I don't know that either company intends to, market this stuff out, to like third parties just yet. Like any of them would with flash memory. Like Intel and Micron have a joint flash memory technology, initiative, and they also sell that memory to third parties. You find the little Intel or the IMFT logo on flash memory and various SSDs that are not made by Intel or Micron. So clearly they sell to third parties. I don't think it's never going to happen. It's just that the stuff's brand new. They can probably barely keep up with the demand right now in the products they're selling, especially with how cost competitive they came out with the 900p, which has more than 480 gigabytes worth of Crosspoint installed onto it, because there's some spare area and there's redundancy and whatnot within the drive. So to be able to make those drives, they have to really, whatever dies they're getting that are usable, whatever their good yield is, needs to go into the products they're making first, making and shipping. So I would imagine once they get better at making it and have extra left over and whatnot, other folks will start wanting to buy it. And yeah, you're right. I think there's a very good benefit in getting it in small quantities, just like what we've seen with what's called the Optane memory part, which is just, it's a little confusing because Optane memory is the stuff in the first place. But the Optane memory product is just one or two of those, chips of Crosspoint installed onto a product. You get 16 or 32 gig used as a cache. It's probably the easiest way to integrate it at the moment and still get a good benefit from it, because you kind of need something very low latency to see the benefit of Optane and Crosspoint. And that's where that Optane memory caching technology comes into play, as as we've reviewed in the past and as it is right now. In the future, yeah, you could end up with almost an ideal SSD in my mind would be super low cost NAND flash memory as your bulk storage stuff, with one or two of those Crosspoint chips on the front end of it acting as a cache. Then you'd have like the best of almost all worlds. It'd be an ideal Steam game drive or something like that. You just have all your games there. They're going to go at least as fast as flash memory goes. But for the stuff that's in the cache, it's going to go as fast as Crosspoint goes. As long as that product has a good interface, it'd have to be like at least a PCIe interface to the rest of the system. So potentially great stuff on the horizon. It just people need to make it. And the controller is going to be more complicated for something like that. You can't take a flash memory controller and expect it to be able to do requests in less than 10 microseconds, which is what Crosspoint can do. So you'd have to make a very fast controller that can handle this cache stuff and at the same time deal with bulk flash memory that's lower cost. Probably get away with products like that just cost the same cost per gig or less than current SSDs and perform way better. So that'd be pretty cool. I'd imagine Intel probably has some kind of plan for that, but for the time being, they have a slightly better margin to make off of just selling, SSDs full of Crosspoint that they already know how to make, that they already have a controller that works. Maybe later on we'll see something more consumer friendly with, less Crosspoint, lower cost, and more flash on it. Let's see here. Nick Carney. I'm hoping for a reduction in price per gigabyte for SSDs. You and me both. And Ryan as well. With Samsung, Intel, and others adding more layers to their V-NAND over time, does that lower the cost to produce each gigabyte, or will only a shrink in process reduce the cost to produce? So the answer there is basically every little thing helps. Every little bit helps, right? But with every one of these new innovations that come out, the innovation itself costs money, right? There's R&D for that. There's 3D NAND is pretty challenging to make. It involves etching. Like, first of all, not only do you build up all of the layers that you want, say it's like 32 or 64 layer NAND, you're building up 64 layers worth of cells. It's for 64 independent layers worth of circuitry that you basically stacked on top of each other. And then part of that process is you have to etch the channels out of the center of them, which is just insane, just technological and material science. And you're etching perfectly straight holes at a nanometer scale down to a fixed depth. And you're doing it across hundreds of thousands of them on a single die. And then once you have those holes etched, you have to somehow form a new material within that void that was left behind from the etching. And it gets crazy. It's like you have crystals at the crystalline structures at the very bottom of each of those channels, and you actually do some process that forces the crystals to expand and travel up the channel. And it's like the material science that goes into that is just outrageous. And all of that costs money, right? That's all R&D. You have to develop all that stuff, all the equipment that's able to accomplish that, right? There's companies just selling the equipment that does the etching of the channels and whatnot. There's intellectual property, there's patents, there's all sorts of stuff all involved with all that stuff. So it's basically just like any other thing that resulted in the last process, like node shrink or any other step. It's just now there's different kinds of steps in addition to the node shrinks. Now, all of this stuff makes it more efficient as far as how much memory you can fit on a given wafer. You end up fitting way more memory, way more capacity onto a given wafer that goes through the fab, so it becomes more efficient in that respect. But you're doing more steps on each wafer. In other words, each wafer has more things that need to be done to it in order to get to that capacity. So, and that's what ends up adding up being how much time each wafer is in each piece of equipment going through the fab, and all that stuff is the thing that's like time is money for that sort of thing. It's not so much the raw material. Raw material cost for flash memory is probably insignificant compared to the work being done on that silicon. All of the time, all of the equipment costs, all of those things, all of the R&D, all the other things that need to be paid off. So, I mean, that's basically the long and short answer is it's just like any other chip thing. All these other improvements we saw to CPU process technology over the years. Yes, you get a faster CPU, but at the end of the day, the cost ends up still, you don't see high performance CPUs, running on the order of tens of dollars or something. Not necessarily. All right. Well, I hope that answers that one. And just like final one to that, like the cost to produce a gigabyte of that flash has gone down. It's just people want bigger and bigger SSDs, and so there's a counter to it. All right, moving on. Dark Wizzy. What performance difference is there with a 960 Pro on PCH lanes, that's the chipset, versus CPU lanes? The answer to that is there's a catch, but if you have only one of them and you only ever intend to use one of them, the answer is very little performance impact. Almost negligible, almost not even noticeable. It's almost not even noticeable with Optane memory connected through a chipset versus through PCIe. There is a latency difference, but it is very, very small, especially on the newest version of the chipsets, like the 370, actually 270 and 370 series chipsets. When you're going through those PCHs, they're just very good at just passing those requests straight through. Because if the drive's not in an array, it doesn't need to do anything with the data. It doesn't need to translate anything. If you request something from it, it basically just passes straight through the chipset right over DMI, which is also PCI Express 3.0 by 4. That's the same speed as the speed going to that single 960 Pro. So it's pretty much a noticeable difference. Now, another couple of gotchas, if you try to RAID several of them together, as soon as you add a second one, you take a latency hit, regardless of what you're doing. Every single request requires a little bit more time to process, because now the chipset has to do RAID calculations and translations and whatnot. Or even if you had a single drive and you say you were doing a lot of USB transfers at a high throughput, USB controller, also through the chipset, also through the same DMI link to the CPU, potentially you're starting to eat away at some of that extra bandwidth that was available. Most of the time the SSD is just going to have that whole DMI link to itself, with nothing else taking any significant amount of throughput. But if your use case is such that you're got a lot of USB stuff connected, you have your Ethernet is also going through there, and that's just saturated 100 megabit. Granted, 100 megabit is, even if you were going gigabit, that could infringe noticeably on the throughput of the SSD. But again, you'd have to be going full speed with the SSD. How often is an SSD actually going over 3 gigabytes per second? Not very often, and definitely not for very long. So the chances are that when it was trying to go fast, the other things in your system are probably not also trying to go fast. So end of the day, probably not noticeable. I personally have, if I'm running a system that has M.2 slot that's connected to the chipset, I don't really give it a second thought. I just put the SSD behind the chipset, and I'm pretty picky about storage performance, so take that for what it's worth. Next question is from the letter I, unless Jim had a typo there in the questions. What is the difference between AHCI and NVMe? So the big deal with NVMe is it's in the name. It was meant for non-volatile memory, right? That's what the NVM stands for out of it. Whereas the AHCI was just advanced host controller. So AHCI was just meant to be an extension on top of the technology that was driving hard disks, because they just wanted the ability to have a queue. There's some other features too, like hot plugging and stuff like that was added as well. But AHCI was just, hey, look, we need the ability for the drive to receive a list of things you want it to do, and so the drive can reorder them and respond to you out of order. In other words, if it can rearrange things in such a way where the head can read from different parts of the disk faster, if you strictly follow the sequence that the computer gave you, it's not the most efficient way to read from a bunch of different spots on a hard disk. So they needed a queue. At the time, they were like, well, queue depth 32 seems like we don't need to go higher than 32. So that's the limit with AHCI. Actually, more specifically with SATA using AHCI. NVMe, they're like, well, first of all, we're not using hard drives anymore. We got a bunch of things that have way lower latencies. And it's getting to the point where the latency, the time it takes for the typical AHCI software stack, in other words, the bits of code in your operating system responsible for translating requests into AHCI protocol, all that stuff is just kind of messy. It's like there's a lot of overhead. There's a lot of calculations have to be done. It wastes excessive time that didn't used to matter because hard drives responding were, take an eternity compared to how fast the computer can make it through all that code. Now you have non-volatile memory things like solid state drives and things with chips on them, and these chips respond way faster than hard disks. So they needed to trim a bunch of the fat from the code base of like AHCI. But at the same time, they wanted to make some other things more efficient. In other words, there's overhead involved with, if the program you're running that wants to request something from the drive is running on CPU number 1. With AHCI, there was only really one thread on the system that handled the storage stuff. And the queue was attached to one of those threads. That thread might not even be on the same CPU as the program requesting the data, which means now you have communication between cores. Every time you want to ask for something, it has to bounce from one core to another. It might not necessarily be running on the very same core. As a matter of fact, it's probably not, right? Because of the kernel, the scheduler would just kind of like, you have AHCI load, it would be like, hey, that's a lot of load. I'll put that on core 0. And then my game is running on core 1. Everything from the game has to now go across to another core, right? Generally not very efficient. The way NVMe works is the queues, first of all, you can have multiple of them. Second of all, you can have one for each thread that's in your system. So if you have a, 8-core, 16-thread system, that system's NVMe driver will be able to have 16 queues, one for each core. And the NVMe device, the SSD itself, can actually handle all of those queues at the same time. So now you're going way above a potential for queue depth of 32 because just, heck, you could even have 32 individual queues with the way that setup is. But again, more efficient because if core 1 now running your game asks for some data, it has its own queue that's already on that same core, right? So it doesn't need to move anything around anymore in order to do that request. So now you're starting to trim off some extra time, and making things more efficient. On top of all that, and this is really, really kind of overkill if you've read any of my articles recently, and you know that even QDepth 32 is really hard to reach with fast SSDs. The QDepth maximum for NVMe is 65,536. It's a 16-bit number. Probably never going to get that high. Most definitely not ever going to get that high. Computer you just don't have enough processing power to throw that many IOs at the storage thing for there to be that many waiting. But they figured, well, why limit ourselves to 32? They wanted to go higher than 32. Fine. Most NVMe things nowadays are rated at QDepth of 256. Still way overkill. But it is what it is. So basically, just to wrap that up, it's just a bunch of different technologies, for a bunch of different interface, not physical interface, but logical protocol improvements to help better deal with non-volatile memory things like solid state things. You Shot My Monkey asks, NVMe RAID on high-end platforms X299 and X399 is a mess right now. Oh yeah. Do you think the inability of AMD and Intel to get their acts together on this will harm the consumer NVMe RAID market? This feature seems to be better implemented on lower-end chipsets, but I would have thought that those most interested in it would also be the consumers intent on running the highest-end chipsets and processors. Yep. Not just yep, but I'm also one of them. Like, I want to run NVMe RAID of more than 3 of those SSDs, and I want it to go fast, and I want it to just work, and I want to be able to do like RAID 5 and stuff like that, so that I can have one of those drives fail and not have to worry about it, right? I don't want to be as aggressive on my backups of my system drive, and maybe I want to throw one extra drive at it for parity and redundancy and failure resiliency or what have you. But yeah, you're very much right. I've spent several weeks beating my head against the wall trying to get AMD RAID to perform the way it's supposed to perform. It's just not doing it. It's not consistent. Intel on the other side, I have had nothing but good experiences with performance consistency. The catch is that what I've been doing is not even supposed to work. Because I've been using 960 Pro drives that are not even supported by Intel in a RAID for VROC. You can install the driver. You can try it out in trial mode. There's a trial mode thing for the driver. You install the VROC premium key and the array goes away because the key is not, even the premium key, the most expensive one, is not, like the system is not validated even with that key to use 960 Pros in an array. So the array actually goes away when you install the key. You're better off just running it in evaluation mode and reinstalling Windows every 90 days. How silly is that? So it's 6 in one, half a dozen in the other. Like, neither side is getting this right. AMD, they've been beating the drum and like tweeting out and, hey, you don't need a key for our stuff. The downside to that is there's a lot of tricks to get the performance anywhere near where it should be, or at least anywhere equal to what Intel performance ends up being. You gotta make sure you're running DDR 3200. You may have to overclock the CPU. You have to set things like memory interleave. You have to change between UMA and NUMA modes. Like, there's all these bells and knobs and switches you have to adjust, whereas the Intel thing just works. And I didn't have to overclock anything, and it just went full speed. But it just isn't validated for the things we want to use it with as consumers, because it was an enterprise technology, right? Also, one other note on the AMD stuff, even though they claim, oh, you don't need a key, they also don't support RAID 5. So it's free. That's nice. It kind of works. There's some security vulnerabilities, as Wendell over at Level 1 Techs pointed out in a recent video he did, which you should check out. But you don't have to install their whole software package. You can make the array in the BIOS and only install the F6 driver, the simple driver, and don't have to worry about any of those weird vulnerability things. But still, it's just like there's so many hurdles on one side, and then it works great, and yet there's a bunch of a completely different set of hurdles on the other side. So yes, it's a complete mess, and you're right. It is not the place where there should be a mess, because this is the high-end equipment that costs a lot of money. Even the VROC key, if you bought one, costs more than $100, maybe even more than $200. If you spend that much, in addition to a motherboard that already costs somewhere around $400 and a processor that may have cost over $1,000, stuff should just work, pretty much. It doesn't. I'm sure it'll get there. But for the moment, we'll just deal with the fact that the cheaper consumer motherboards, which are DMI limited, meaning that there is a bandwidth restriction, work great with up to 3 drives in NVMe RAID, and you can even do RAID 5, and it all just works, and it's really good. That's on the Intel side. Anyway, Marlo Mitchell, other than the usual stuff like SSDs and GPUs, are there any other products or innovations on the horizon that you're really excited for? Probably whatever the next generation of VR and AR stuff's going to be. I've toyed around with like a Rift and a Vive, and they're all cool, and there's games for them, and there's things to do with them, and that's nice, but it's like the software, the amount of stuff that's out there for it has kind of leveled off, and I just feel like there is a huge amount of untapped potential in that space. Just different ways of inputting things, like I'm visualizing the whole Minority Report, insert sci-fi movie where somebody is just doing something cool and designing something or coding something or doing, whatever in VR. It's just that it's not that there's none, but there's very limited tools right now. So I think that we need another generation or two of this stuff to come out in order to kind of spur more software. Like, the hardware leads software usually, right? You need the hardware. Nobody would have made any VR games if you didn't have these things in the first place to run the games on, right? So maybe we need, some newer generations of this stuff to come out, spur up a little more excitement, and maybe try to get us on that kind of exponential curve of iterate and develop and make things better and better. But again, we're not there yet. Hopefully we'll be there soon. That's where I see excitement for in the future. Anyway, that was the last question. All right, so make sure you guys leave comments on either the bottom of this video. Jim will pick them up there, or just if you're watching this video on PCPer, leave a comment in the article, and we'll filter stuff out there too. And with that, I'm Allyn Malventano, and I'm out of here. See ya.